Good afternoon. We start our 11th chapter in the textbook, Dual Nature of Radiation and Matter. And today we will discuss that topic, photoelectric effect, from that chapter. Now, certain metals, when light is incident on these metal surfaces, if the light has a minimum energy, then these metal surfaces emit electrons, and these emitted electrons are called photoelectrons, and this phenomenon is what you call as photoelectric effect. Alkali metals like sodium, potassium, lithium, they give out photoelectrons or emit photoelectrons when visible light is incident on these metal surfaces. So when light is incident on a metal surface, if the minimum energy condition is satisfied, then they emit photoelectrons, and this effect is what we are going to discuss today as photoelectric effect. Towards the end of the 19th century, wave theory was well accepted, and most of the phenomenon, like we learned, interference, diffraction, polarization, all of them were explained using the wave theory of light. But certain basic features of photoelectric effect could not be explained using the wave theory. So in 1905, Einstein put forward the new picture of electromagnetic radiation, in which he said electromagnetic radiation consisted of quanta of energy or packets of energy, which he called the photon. And first thing to note is that each photon, each packet of energy of this electromagnetic radiation had an energy which was equal to h nu, which is therefore equal to hc by lambda, because you know nu is equal to c by lambda. So every packet or every photon has an energy which is equivalent to hc by lambda. Also, these photons carried momentum, and the momentum of a photon was given by h nu by c, where again nu is the frequency of the incident radiation and c is the velocity of light in free space. Then the third point that you need to know about a photon in this photon picture of light is that the intensity of the radiation or electromagnetic radiation, the intensity depended on the number of photons emitted in 1 second crossing per unit area. Like if you have a light source, and if the light source is incident on an area, the number of photons incident per unit time per unit area determines the intensity of the incident radiation. Also, so that means the energy of the incident radiation, which we know depends only on the frequency. It means that the intensity, increasing the intensity of the incident radiation does not have any effect on the energy, because the energy clearly depends only on the frequency. And intensity, if you increase the intensity of the electromagnetic radiation, please understand you are only increasing the number of photons in 1 second in unit area, but not increasing the energy of each photon. Energy of each photon depends only on its frequency. And also, the photons are neutral. They are not electrically charged, and therefore they cannot be deflected using an electric field and a magnetic field. So I hope these points that we have discussed here is clear to you, because we need to know these points in order to study the photoelectric effect. So I hope one thing is very clear to you, that intensity determines the number of photons, frequency determines the energy of the radiation. Now, work function. I told you that there is a minimum energy condition for the metal surface to emit the photoelectron. So every metal surface has a minimum energy condition, which is called as the work function phi. Work function phi 0, which is also energy. So this is going to be equal to h nu 0, and this is also nu, you know, is equal to c by lambda. So we may also write it as hc by lambda 0. Okay, work function is therefore the minimum energy that a incident radiation must have in order to produce photoelectric effect from a metal surface. For example, let us take potassium metal. Its work function is 2.30 electron volt. So if your incident radiation, whose energy as we know is equal to h nu, has, let's say, only 2 electron volt. If it has only 2 electron volt, then its energy, the work function, the minimum energy required for this metal surface to emit an electron is 2.30. But your incident radiation is carrying only 2 electron volt, which means it is not having enough energy to produce this photoelectric effect, and therefore no electric effect will happen. This metal surface will not emit a photoelectron because the energy of the incident radiation is less than the work function. But if let's say this one has more than, let's say this has 4.30 electron volt. So the incident radiation now has an energy greater than the work function, and therefore this incident radiation will produce photoelectric effect on this metal surface. So work function, as you see, is the minimum energy required for a metal surface to emit photoelectrons when incident light is falling on that metal surface. Electron volt, you will see, is a very commonly used unit of energy in nuclear physics. 1 electron volt is the energy acquired by an electron when it is accelerated through a potential difference of 1 volt. As you learned in the second chapter, the potential energy of an electron when accelerated by a potential difference is given by Q times V, where V is the potential difference. That is work done on unit charge. So if you have a Q charge, then the total work done, that is potential energy, will be Q times V. So we have an electron here. So the charge on the electron is 1.6 into 10 raised to minus 19. And if it is accelerated with a 1 volt, then this is going to be equal to, the potential energy is going to be 1.6 into 10 raised to minus 19 joule. And this is what we call as 1 electron volt. So 1 electron volt is equal to 1.6 into 10 raised to minus 19 joules. The work function for platinum is the maximum. Work function maximum is for platinum, which is 5.65 electron volt. And the work function minimum is for cesium, which is 2.14 electron volt. So these are the work functions, that is the minimum energy required for a metal surface to emit photoelectrons, and that is given in electron volt. So naturally, when there is a concept of minimum energy, then there is also a minimum frequency of the incident radiation that will produce photoelectric effect, and that minimum frequency of the incident radiation that will eject electrons from the metal surface is what you call as threshold frequency. So that means because the energy and the wavelength are inversely proportional, this is called the threshold wavelength, which therefore happens to be the maximum wavelength of the incident radiation that can produce photoelectric effect. So you need to know the definition for work function, threshold frequency and threshold wavelength. And of course this phenomenon called photoelectric effect. Now we have Einstein's photoelectric equation. So just now I showed you that if this potassium has a work function of 2.30 electron volt, I told you. So if the incident radiation is carrying an energy h nu which is equal to 4.30 electron volt, then out of this 4.30 electron volt, we see that 2.30 has been used up to emit the photoelectron. So the emitted electron must carry the remaining, that is 2 electron volt, as its maximum kinetic energy. So the maximum kinetic energy of the photoelectron emitted will now be 2 electron volt, because from this 4.30, 2.30 is used up to emit the electron. The remaining is given as the remaining 2 electron will be given as the kinetic energy to the emitted electron. So you may write, this is the total energy of the incident radiation, which is h nu. This is equal to, this is the work function of the metal surface, plus this is the kinetic energy maximum of the emitted photoelectron. The photoelectron can have an energy less than this, because after when the incident radiation strikes the metal surface and the electron absorbs that energy, due to internal collision it may lose some of its energy, and then when it is ejected it may not have this 2 electron volt. It may have an energy less than that. Anyway, this is the maximum kinetic energy that the emitted electron can have. This is just an example. So this is what we have as Einstein's photoelectric equation. H nu equal to phi 0 plus kinetic energy maximum of the emitted photoelectron. So this nu is the frequency of the incident radiation. H is the Planck's constant. Phi 0 is the minimum energy requirement, that is work function required to emit a photoelectron, and the remaining energy will be given as the kinetic energy of the emitted electron. Now, knowing all this, we may now go into the experimental study of the photoelectric effect and also study the graphs in this experimental study. Okay. Now, for this experimental study, we have a evacuated tube. An evacuated tube with a small window through which incident radiation can fall on we have a small window here which can allow light to enter so that it falls onto a photosensitive plate, and this photosensitive plate is called the cathode, or it's also called the emitter. And we also have another plate here, a metallic plate called the anode or the collector. And these two are then connected to an external circuit. I'm not drawing the whole circuit. The whole circuit is there in your textbook. So I'm just drawing a battery here, a cell. Now this cell, we have got the anode connected to the positive terminal and the negative connected to the negative cathode here. So that this is at a negative potential and this is at a positive potential. There is a potential difference between the two plates, the cathode and the emitter and the collector. This is also called the collector. Now this, you can switch the terminals of the battery using a commutator, and that figure is there in your textbook. Okay. So when light is now incident on this metal plate, let's say light is incident on the metal plate, it's a photosensitive material, and if the light has an energy which is greater than the work function of this metal, surely that metal is going to eject photoelectrons, and the ejected photoelectrons are now going to travel towards the positive plate, because you see there is an electric field here, and the electric field is directed from the positive to the negative. Electrons always move in a direction opposite to the electric field. So these electrons are repelled by this emitter here, attracted by the positive anode, and they move towards this with a certain kinetic energy. Kinetic energy dependent, as you know, from, you know this equation, H nu equal to phi 0 plus the kinetic energy maximum. So maximum kinetic energy will be dependent on the frequency. Okay, so these electrons are taken in by the collector and you have a photo current in the circuit. Now our first graph, let me clear this. Our first graph is to study the variation of the photo current. I am plotting the photo current along the y-axis and the intensity of the incident radiation along the x-axis. Okay. Now intensity, I told you, is the number of photons emitted in unit time for unit area, crossing per unit area. So intensity decides the number of photons on the incident radiation. So let us imagine that this intensity, this has 100 photons. Okay, this incident radiation has 100 photons. One photon will release one photoelectron. So if 100 photons are incident on this, then 100 photoelectrons are going to be emitted by the emitted by this photosensitive plate. So you see, as you increase the intensity, the number of photons are increasing, and therefore number of photoelectrons will increase, which will definitely increase the photoelectric current, and therefore we have a straight line graph showing you that the intensity is, the photoelectric current is directly proportional to the intensity. So I hope this graph is clear to you. If you increase the intensity of the incident radiation, we know the number of photons will increase, If the number of photons increases, the number of photoelectrons also will increase, and that increases the photoelectric current, and therefore this graph shows you the photoelectric current is directly proportional to the intensity of the incident radiation. The next thing that we are going to study here is the variation of one second. This is the anode and this is the cathode. Okay. The variation of photoelectric current. So we have the photoelectric current here along the y-axis with the anode plate potential. So this is the anode plate potential or the accelerating potential. The potential between the two plates is the accelerating potential. The electrons being accelerated by that potential. So we're going to study the variation of the photoelectric current with respect to the potential that we're going to apply to the anode. Now, in our example, we have taken the intensity of radiation to be 100 photons. The number of electrons emitted in 1 second therefore will be 100 photoelectrons. Now, as I go on increasing the plate potential here, it means that the accelerating potential is increasing, and as it increases, more and more electrons are taken in by the anode in 1 second. So, as you increase the anode plate potential, more and more electrons get that kinetic energy and they reach the anode, and the photoelectric current will go on increasing. So let me show you. Let me start from here. It goes on increasing. When you reach a particular potential, anode plate potential, let us imagine that all the 100 photoelectrons that are emitted are taken in by the anode, are collected by the anode. Now, if you increase the anode plate potential, you cannot increase the photoelectric current because this plate is emitting only 100 photoelectrons in 1 second. So, even if you increase the anode plate potential, you are unable to get more than 100 photoelectrons. So, the photoelectric current will remain a constant after that. So, once you reach that point or that particular potential of the anode, when all 100 photons are being collected in 1 second, all 100 photoelectrons are being connected in 1 second, after that, even if you increase the anode plate potential, there is no use. You do not get larger photoelectric current because there are only 100 photons incident here. This is emitting only 100 photoelectrons, and therefore the anode plate can only accept 100 photoelectrons in 1 second. Now let us imagine that using the commutator, I am going to reduce the plate potential on A. So I am going to reduce the plate potential on A slowly, and as I reduce the plate potential, you see the accelerating potential is decreasing. So the number of photons accepted by the anode in 1 second will also decrease. For example, let's say this when I reached, I'm just giving a random example. Let's say when I reached 10 volt, all 100 were accepted. Now if I reduce it to 9 volt, surely the number of photoelectrons accepted also will reduce. Let's say out of the 100 that are emitted in 1 second, only 90 electrons are accepted. So the photoelectric current goes on decreasing. Now suppose I bring this plate potential to 0. So this is 0 volt. The photoelectric current will not drop to 0 because with respect to the anode, with respect to the cathode, the anode is positive. 0 is positive with respect to this. So for an electron, with respect to the cathode, since the anode is positive, it will still accept electrons, but the number of electrons accepted will be much smaller. So the photoelectric current also is lesser. So even though you brought your anode plate potential to 0, it is still positive with respect to the cathode, and therefore still photoelectrons are being accepted by the anode. So the photoelectric current does not drop to 0, but will be much lesser than this value. This value is what you call as the saturation current. So the saturation current, I hope you understood, depends on the intensity. Because we had 100 photons here, this saturation current value will depend on the intensity. If I have 200 photons here, then the saturation current would have been larger, and therefore that's why I told you the value of that saturation current depends on the intensity here. So now we are reducing the anode plate potential. Therefore, the number of photoelectrons accepted by the anode is also decreasing, and therefore the photoelectric current is also decreasing. Now from here, using the commutator, suppose I start giving a negative potential to A. As I start giving a negative potential to A, naturally this anode is now starting to repel the electrons. As I start repelling the electrons, I told you these electrons, some of them will have very less kinetic energy and they will be repelled initially. The ones which have larger kinetic energy will still reach the anode and be accepted. So as you start making this negative, the few of these electrons start getting repelled. So the number of electrons accepted by the anode will decrease and therefore the photoelectric current will further decrease. At some negative potential of the anode, at some value of this negative potential of the anode, even the electron with the maximum kinetic energy will be repelled, and then you will see that no more electrons are accepted by the anode, and that negative potential that is given to the anode at which all photoelectrons are repelled, that is there is no more photoelectric current, is what you call as the stopping potential or the cutoff voltage V0. So how do you define this V0? V0 is defined as a negative potential given to the collector or the anode. This is called the emitter and this is called the collector. So stopping potential or cutoff voltage is defined as the negative voltage given to the collector at which the photoelectric current becomes zero. That means all the electrons are repelled and the photoelectric current reduces to zero. So this stopping potential is also called cutoff voltage. Now, when does this happen? That's what we're going to check. The electrons are coming forward with some kinetic energy, and when the maximum kinetic energy becomes equal to the energy with which the collector is repelling the electron, that is when there is no photoelectric current. They're all repelled back. So this is going to be equal to EV0 because you know the potential energy with which it is being repelled. The potential energy is given by the formula Q times V, which we already learned in the second chapter. Now it is an electron that is approaching the collector. So I have replaced this Q charge with electronic charge, and I told you the potential at which this happens is called the stopping potential. So this V has been replaced by the stopping potential or the cutoff voltage. So when the kinetic energy of the approaching electron, maximum kinetic energy of the approaching electron becomes equal to the potential energy with which it is being repelled, then no more electrons are accepted and the photoelectric current becomes zero. So this is the condition. Kinetic energy, the maximum kinetic energy of the approaching electron must become equal to the potential energy with which it is being repelled by the collector, and then at that point the photoelectric current becomes zero. So we may also write Einstein's photoelectric equation as h nu equal to, this was our Einstein's photoelectric equation. So h nu equal to phi 0 plus, instead of kinetic energy maximum, you may also replace it with EV0, where nu is the frequency of the incident radiation, phi 0 is the work function of this photosensitive plate which is emitting the photoelectron, E is the electronic charge, and V0 is the negative potential that is given to the anode plate or the collector plate when the photoelectric current reduces to zero. So you will see from this equation that this frequency is actually directly proportional to the stopping potential, or this you also know is the maximum kinetic energy, that is half mv square. So frequency of the incident radiation can changes the stopping potential and the kinetic energy. So when we study this next two graphs, please understand, whenever you talk about changes in intensity of the incident radiation, that is intensity means the number of photons present in the incident radiation, please remember that this can have an effect only on the number of photons in the incident radiation, which means it is determining the number of photoelectrons That means it is determining the photoelectric current, which we saw in the first graph. The intensity and photoelectric current are directly proportional. Greater the intensity, greater will be the photoelectric current. Second thing is, whenever we increase the frequency of the incident radiation, you see from Einstein's photoelectric equation, this is a constant. So if you increase the frequency, you are increasing the kinetic energy of the emitted photoelectrons, and if you increase the kinetic energy, you are increasing the stopping potential V0 or the cutoff voltage. So you need to know very clearly that the frequency has no effect on the photoelectric current because frequency cannot change the number of photons. So frequency has no effect on the photoelectric current, and change in intensity does not affect the kinetic energy or the stopping potential, because you see it is only the frequency of the incident radiation that is changing the kinetic energy and therefore the stopping potential. So whenever you have an application question or when we are discussing the graph, remember, change in intensity of incident radiation changes the photoelectric current, the number of photons, and therefore the photoelectric current. Change in frequency of the incident radiation changes the kinetic energy of the emitted electrons. It also changes therefore the stopping potential, and that is what you need to keep in mind. So now if we are going to plot a graph where we are going to the same graph that we did now, where we have the photoelectric current on the y-axis and the anode plate potential or the collector potential on the x-axis, and you're going to plot a graph of the two where we know the graph is going to look like this, where this is called the saturation current, and I told you that the saturation current actually depends on the number of photons, that is the incident the intensity of the incident radiation. So here, if I'm going to use three different intensities, three different light of different intensities but same frequency. Okay, I'll just clear this. We have three different light falling on the photosensitive plate, that is I3 greater than I2 greater than I1. Okay, but all of them have the same frequency. Then the moment you see this, you need to know frequency same would imply that the stopping potential is the same, the kinetic energy of the emitted electrons are the same. So stopping potential will be same, kinetic energy will be the same. But three different intensities would mean there are three different, the photoelectric current is going to be different, because the intensity determines the intensity is directly proportional to the photoelectric current. So in your graph, you will see that this is how it will look, where all of them have the same stopping potential because they all have the same frequency, but they have different photoelectric current because the intensity is different. So greater the intensity, greater the saturation current. So this is I2 and this is I1. So I3, when the intensity is greater, the photoelectric current, the saturation current is also greater. So this is a graph that represents variation of photocurrent with anode plate potential for radiations, three different radiations having the same frequency but different intensity. The same thing we are going to draw for three different radiations which have the same intensity. So we are now going to keep the intensity same. Intensity same. The moment you see intensity same, you should remember that the saturation current is going to be the same, because I told you the intensity determines the saturation current, the photoelectric current. But they have three different frequencies such that nu3 greater than nu2 greater than nu1. Greater the frequency, I told you, greater the kinetic energy, greater the stopping potential. So minus V03 must be greater than minus V02 must be greater than minus V01. So that when you plot the graph where we have this as photocurrent and here we have the anode plate potential, you will see that the saturation current is going to be the same because they all have the same intensity, but they have three different, they will have three different stopping potential: minus V03 greater than minus V02 greater than minus V01. Do not bother about the negative sign. You look at the magnitudes. That's why I said greater the frequency, greater the stopping potential. Look at the magnitude. The negative sign shows you that it is a negative potential that is applied to the anode plate. So you will see that the saturation current will be the same for all the three different because the intensity is the same. Okay. Then the last graph that we need to discuss under this topic is this graph where we're going to plot we have this has the frequency along the x-axis and we have the stopping potential. So this is a variation of stopping potential with frequency. Okay. Now the equation, Einstein's photoelectric equation, we know h nu is equal to phi 0 plus E V 0. Now if I divide throughout with E, you will see this is h by E into nu is equal to phi 0 by E plus V0, or I may rewrite this equation as V0 equal to h by E into nu minus phi 0 by E, right? Now this V0 is a variable along the y-axis. So I may write this as y equal to h is Planck's constant, E is electronic charge, therefore h by E is going to be a constant. I will take it as m, constant. Nu is the variable along the x-axis. So this is x plus, you have a constant here because work function for a given metal is a constant. This is electronic charge. So y equal to mx plus c, which shows you that this represents a straight line. Now the y-intercept should be a negative intercept, phi 0 by E. So if I now draw now you will see that the two lines, let's say this represents metal A and this represents metal B. You will see that both the lines, whichever metal you may take, the slope of the line given by h by E is a constant. If you compare, you will see that the slope of the line is given by h by E, which is definitely a constant because Planck's constant and electronic charge. So any metal you may draw will give you parallel lines having the same slope. But this is a negative intercept, so we have this as the negative intercept. The negative y-intercept here will be phi 0 by E. Greater the work function, greater will be the negative intercept. Also you will see along the y-axis, this is the minimum frequency for the different metals. So that is the minimum frequency for which you can have photoelectric effect or photoelectric emission is what you call as the threshold frequency, which is different for different metals. You will see in this case, metal A has a smaller threshold frequency. So you can't have your line starting from 0, which would mean that the frequency is 0. At 0 frequency, so every metal has a minimum value of frequency for photoelectric emission to happen, and that minimum value is what you call as threshold frequency. From our graph, you will see threshold frequency of metal B is greater than that of metal A, but all of them will be parallel lines because the slope of this will be the same. And this will give you the y-intercept, the negative intercept will be work function by electronic charge. Okay. So this is the last graph that we need to discuss in this chapter. So from this, all these discussions, we have arrived at certain conclusions. From the first graph, what we arrived at, our conclusion is that the photoelectric current is directly proportional to the intensity of the incident radiation. I repeat, because the intensity determines the number of photons, therefore number of photoelectrons, and therefore the photoelectric current. Then we also came to the understanding. Second one is that from Einstein's photoelectric equation, H nu equal to phi 0 plus EV 0, which is also the kinetic energy maximum. The frequency, changing the frequency changes the stopping potential and therefore the kinetic energy of that incident radiation. Also, every metal has a minimum value of threshold frequency, minimum value of frequency for which photoelectric emission takes place, and that is what you call as the threshold frequency. Then we also know that the photoelectric effect is an instantaneous process. That means as soon as the light is incident on the metal surface, if the energy of the incident radiation is equal to or greater than the work function, the photoelectrons are immediately ejected from the metal surface without any time lag. There is no time lag, and that is why this is called an instantaneous process. Also, the intensity has no effect on the kinetic energy of the emitted photoelectrons. Only the frequency of the incident radiation can increase the kinetic energy and therefore the stopping potential of that emitted photoelectrons. Okay, thank you and good night.